Hello, my name is Yelda Gin and I'm a PhD candidate at the Center for Natural Material Innovation in the Department of Architecture at the University of Cambridge. I will present our paper titled Robotic 3D Printing with Earthen Materials as a Novel Sustainable Construction Method, authored by myself, Biçer, and Dr. Michael Ramage. The construction industry was responsible for 39% of energy and process-related carbon dioxide emissions in 2018. 11% of those emissions were caused by manufacturing building materials like cement, steel, and glass. The rising demand in construction is widely supplied by concrete and steel, worsening the impact of the construction industry on the environment. Building with earth is a time-tested environmental construction method. There are several benefits of building with earth. Earth is carbon neutral because unlike concrete or steel, it requires no industrial processing or energy-intensive processes to transform into building materials. It is also local and available worldwide, which saves from the energy used for transport. Earth is circular because it can be reused indefinitely or can go back to nature at the end of its life cycle, so it creates no waste. Earth provides comfort and health because it's energy efficient, stores heat due to its thermal mass, and balances humidity indoors. It's also a non-toxic and non-polluting material. Cob is an energy-efficient conventional earthen building technique which consists of mixing clayey earth and fibers such as straw or grass and then applying them by hand with pushing them to create a monolithic wall. Cob has been gaining interest from researchers as a promising sustainable building technique for contemporary architecture. Cobage, for example, is an international research project led by the universities in France and the UK, aiming to develop a novel low-carbon cob building technology and subsequently get it registered in building codes. Robotic 3D printing with earth presents an alternative for the future of earthen architecture, as it's a fast and labor-saving process which makes it favorable for high-income countries. It does not need scaffolding and is mostly waste-free. Compared to the conventional earthen building methods, robotic 3D printing uses less earth and provides geometric freedom to fabricate advanced forms which can enhance the thermal and structural qualities of the building. For 3D printing with earth, a more fluid mix than the conventional cob mixes is required to assure the flow of the material through the printing system. However, additional water content also causes cracking and shrinkage while drying. Too much water also prevents layers to dry quickly to be robust enough to carry subsequent layers, which causes collapses during printing. Hence, adding optimal water percentage to the mix is crucial. Fiber contents which are used to strengthen the mix should also be smaller than the traditional cup mixes to avoid blockages through the extruder and the nozzle. Extrusion rate, layer height, and extrusion speed should be adjusted based on the properties of the earth mix. Electromechanical and pneumatic systems are the two main extrusion systems used for printing clays and earthen materials. The electromechanical system uses a stepper motor which is connected to a warm gear reducer to push the clay along a cartridge into the extruder. Auger screw transports and compresses the material to the nozzle. The size of the container within the extrusion system limits the size of the printable object. With this system, the need to replace and relocate the containers during the printing process disrupts the continuity of the printing and requires extra labor force. Keeping the form stable during the extrusion process is challenging due to the increase in loss. Similar to the conventional wet earthen building methods, a drying period should be considered at intervals for the material to settle and gain strength. Although creating overhangs is hard with 3D printing earthen materials, recent research has demonstrated that it's possible to achieve 40 degrees of straight inclination with 3-axis 3D printing, while 45 degrees of radial inclination is achievable with 6-axis 3D printing. Once again, extrusion rate, layer height, and extrusion speed should be adjusted based on the geometry. Although mass customization, additive manufacturing, robotics, and automation in construction are currently not mainstream, and doing it with earth is even less so, it is still a promising alternative for the future. Our ongoing research aims to contribute to this field and its adaptation to the industry, considering the opportunities and challenges presented in this paper based on the recent research in the field. There are several benefits such as using local soils and excavation soil where possible for on-site robotic printing as an energy-efficient and affordable construction process for the future of construction. Concrete 3D printing has been gaining interest in the construction industry. However, 3D printing with earthen material is a more sustainable option. There is no post-processing requirement, such as firing for 3D printing for earthen materials. There are also several challenges to be addressed. Unlike concrete, earth is not a standardized material. The properties of subsoil varies based on the location and needs to be tested in each occasion. Material mix ratios and fiber sizes requires adjustments based on the extrusion system and nozzle diameters. It's essential to monitor flow rate, flow speed, geometric performance, and a drying speed during the printing and enhance these parameters subsequently to ensure an optimum printing process. Strategies are expected to be developed for introducing fenestrations, overhangs, and connection to foundations. As the continuity of the printing depends on the capacity of the container, continuous feeding systems should be designed based on the size of the building. Considering the cost of industrial robots and complexity of the software to operate them, developing affordable robotic printing systems and accessible software can accelerate adoption of this system as a mainstream construction method. Thank you for listening.